Two ways to calculate acceleration. That's what we're going to look at in this video. But firstly, we need to understand what acceleration actually is. So acceleration is speeding up, slowing down, and even changing direction, which we'll get into later, not in this video. But in its essence, acceleration is the rate of change of velocity. So that is effectively per unit of time. So it's how quickly velocity is changing will equal the acceleration. So it's the rate of change of velocity, how much it changes in a particular time. So mathematically, if we put that into an equation, we end up with this in this box here, which shows us that the acceleration is equal to the change in velocity divided by that time taken. And we need to unpack that a little bit to work out how we're going to calculate this change in velocity. Okay, so the change in a quantity in physics is usually given by the final number, or in this case the final velocity, minus the initial velocity. Okay, the final velocity minus the initial velocity. Now, obviously, we can't put v for both of those quantities. We can't have v minus v. So we need different symbols for the two quantities. And the symbols we use are v for the final velocity and u for the initial velocity. So it's the letter before v, effectively, because the initial comes before the final. So the change in velocity, which is the final minus the initial velocity, is going to be equal to v minus u. So v minus u is the standard shorthand for the change in velocity. Sometimes in some courses you find v minus v naught, where v naught is given for the initial velocity. We're not going to use that, we're going to use v minus u. So if we look down here at this, the symbols of this equation here, we can see that we have the standard symbol a for acceleration, and then we have v minus u for the change in velocity, which is the final velocity minus the initial velocity, and finally divided by t, which is the time. In terms of the units of acceleration, acceleration is measured in meters per second squared. Okay, the reason for that is we have change in velocity, which is meters per second, divided by time, so divided by seconds again. So we have meters per second. If we use the rules of indices to rearrange that, we find that that is equivalent to meters per second squared. Now that square has no bearing on the numbers themselves, it's just part of the unit, it's just that you've got two lots of seconds underneath, so rather than write seconds times seconds, we write seconds squared. Okay, so meters per second squared. So here's some nice easy questions using that equation. Now notice that we have time in this one, we have time, so we're looking at how long things are taking. A car accelerates from rest is a standard word for stationary, to 30 meters per second in 15 seconds. So let's identify the quantities and then work out the acceleration of the car. So it's from rest to 30. So rest is going to be the initial state of the vehicle, so that's going to be u, the initial velocity, and 30 meters per second is going to be the final velocity, v. 15 seconds is obviously the time that takes. So we have our u, v and t, and then we just need to put it in the right boxes. So a is equal to v minus u over t, which is going to give us 30 minus 0, we'll just put that in for completeness, divided by 15. So 30 over 15 is 2 meters per second squared. So that's a nice easy example of how to use that one. Here's another one, virtually identical, except this one has a non-zero initial velocity. So a car goes from 15 to 35 meters per second in 5 seconds. So this one's going to be u, this one's going to be v, and this one's going to be t. So again, same procedure, a is equal to v minus u over t, and in this case what we get is 35 minus 15 over 5. 35 minus 15 is 20, so 20 over 5 is 4. So the acceleration of that particular car is 4 meters per second squared. Okay, so that equation there allows us to calculate acceleration very simply if we know the time taken. But what if we don't know the time taken? What if we have two posts separated and rather than having a stopwatch we have a meter ruler or a trundle wheel or something like that we can measure distance with? Is there a way to calculate acceleration when we don't know how long the change in velocity has taken? Well, yes, there is. It's slightly more complicated, but let's have a look at that. So if we know the distance rather than the time, and we can also work out the velocities at the beginning and the end, then we can use this equation to calculate the acceleration, or indeed any of the other quantities in the equation. So here we are. Let's just zoom into this a bit, because there's a bit of detail here that I don't want you to miss. The equation is the final velocity squared minus the initial velocity squared is equal to 2, which is just the number 2, multiplied by the acceleration, multiplied by the distance moved. Okay, so here we have distance moved instead of time. So this one, we will use this one when we know the distance that the object has travelled rather than the time that it's taken to go from the initial to the final velocity. And the final velocity and the initial velocity are squared, and this is not just in the unit now. Obviously units of acceleration are still meters per second squared, but that's not related to the final velocity and the initial velocity. You have to actually square the numbers in this one. So looking at that in symbols, that's down here. We have v squared minus u squared is equal to 2 times a times x. And here we're using x as the distance travelled or the distance moved rather than d. Okay, so we've got v squared minus u squared is equal to 2 times a times x. This is a much more complicated equation. You don't have to remember this one. It's given to you in the back of the exam paper as a provided equation, but you do have to know how to use it and also how to rearrange it. So let's have a look at these two examples of that, and then we'll see if we can have a go at rearranging it as well. So here's an example. Find the acceleration of a car that goes from 10 meters per second to 30 meters per second over a distance of 400 meters. So it's going from this, so that's initial, to this, so that's final, and this is x, the distance, and we want to find the acceleration. So straight away we have to rearrange it. So let me help you with that. We have v squared minus u squared is equal to 2ax, and we want to find a. That's what we want to make that the subject of our equation. So a is multiplied by both 2 and x, so what we're going to do is divide both sides by 2x, and that will leave a on its own, which will give us a is equal to v squared minus u squared divided by 2x. So now we have our equation that we can use rearrange to find the acceleration, which is what the question asks. So let's plug the numbers into that. V is 30, so we want 30 squared, don't forget the squares, minus the initial velocity is 10, and we want to square that one as well. So 30 squared minus 10 squared divided by 2 times 400. 30 squared is 900, 10 squared is 100, so effectively we get 800 divided by 2 times 400, which is also 800. So this all boils down to an acceleration of 1 meter per second squared. Okay, so that's quite a good exemplification of using that equation when we know the distance. This one's exactly the same, so I'm not going to go through that one as well. Same things, just different units. Don't forget to square the speeds. Here we want to know the final speed of a ball being dropped from a height of 15 meters if the acceleration by gravity is 10 meters per second squared. So we know that the acceleration is 10. We know that the distance it's fallen, which is vertical in this case, it's a height 15 meters. And we want to know the final speed, so we want to know v. So we've got everything except for u. There's a hint to what u is in the question because the ball is being dropped, and if it's dropped it's held still and then let go. So we know that the initial speed must therefore be 0. Okay, so we want to find the final speed. Okay, so let's have a look at that. Right, there are two ways to approach an equation that needs rearranging. The first way is to rearrange the algebra first and then put the numbers in. Or you can put the numbers in and simplify it using the number crunching of the arithmetic and then rearrange for the answer. So that's the way I'm going to approach this one. I'm going to write down the equation v squared minus u squared is equal to 2ax. Again, this time I want to find v. Not v squared, but v on its own. I don't know that. So let's put the numbers in at this point and then see how we get on with that. So we don't know v, that's the one we want, so v squared minus u is 0, so 0 squared is just 0, is equal to 2 times the acceleration, which is 10, times the height that it's fallen, the distance that it's fallen, which is 15. So when we simplify that, I'll just do it on the calculator so you can see what I'm doing. 2 times 10 times 15 is 300. So we know that v squared, ignoring the minus 0 because that cancels out, is equal to 300. So it's quite simple to get to that point, and then we just take the square root of both sides, which will give us v is equal to the square root of 300, and we can find that here. Oops, let's just start again there. 300, whoops, sorry, I've learned to operate my calculator. Square root of 300 equals 17.3. So the final speed is equal to 17.3 meters per second. Okay, so that gives us two ways to calculate acceleration. One, when we know the time, let's scroll back to our first one. The acceleration is equal to the change in velocity divided by time, v minus u over t. And one where we know the distance. And the one with the distance is this one. V squared minus u squared is equal to 2 times a times x, where x is the distance. The first one you need to remember for the exam. The second one is given to you.